Alexander Fabian Impertro has joined the meeting. Alexander Fabian Impertro has left the meeting.
I get to use pilots. Does this work? Yeah. There you go. And now it should be. Right? Yeah, now it should be on. I should be.
Okay.
But we can double check before we start, just so that we don't have to interrupt in the middle of the talk. It is actually part of the ERT. Yeah. No, the title of the ERT, I think, is really many others. Okay. I don't remember. I'm waiting for those guys. I can't. That's for questions. And if you want to turn it on, there's the red button. Okay. And the button will I hope it is. I mean, we should probably. And is the mic working? Is the microphone working? Yes. Yeah. Okay. Good. Yeah. Because I can't hear from here. Okay.
Okay.
So, I guess we can start. Welcome to the last session of the morning. Apparently, we just had a discussion. So we start with Marin Bukov talking about locate theory as a concept.
Thanks a lot. I'd like to start by thanking the organizers for having me here, for also making the effort to set up such a nice workshop. I will talk about the work in progress today. So any kind of feedback that you guys want to give me is much welcome. And so this is work that is done with my PhD student, Paul Schindler, at the Max Planck for Complex Systems in Dresden. And as you can tell from the title, this is going to be a talk about periodically driven systems. And so the first question that we may want to answer is why we should care about periodically driven systems. Now, I realize that, with these organizers and in this audience, maybe we don't require much of a motivation for this. So I'm going to just cut it short. We have seen a bunch of examples where periodic drives actually are quite handy. And in particular, one of these examples is flow K engineering. So, there was a talk yesterday by Alejandro about artificial gauge fields. Then there were other talks about topological matter. I think we will hear about time crystals very soon. So this is all, under quantum simulation. But of course, periodic drives occur in quantum computing. For instance, if you've heard about trotterization or trotter dynamics, this is one example of a periodic drive. And they also can be handy for quantum sensing. And so the question that I want to ask today is how do we manipulate periodically driven systems? And I actually want to try and give you kind of a non-standard view of flow K systems. So this is going to be more like a theory talk. So I'd like to put like the main message here up front. So in the next 25 minutes, I'll show you how flow K theory can be derived from the adiabatic theorem. And if that sounds weird to you, that's good, because it's not straightforward. We'll see how that comes about. To do this, I will first review flow K theory. We'll talk about flow K Hamiltonians and micromotion, flow K states and quasi-energies, because we're going to need some of these objects later on. But then I also need to talk about adiabaticity, and in particular, I will need the concept of counter-adiabatic driving, and so we'll go into the definition of gauge potentials and the like, and then we'll put the two together and prove the statement that is written here in the purple box. All right. So about 150 years ago, flow K showed that the time evolution operator of an ordinary differential equation with time periodic coefficients factorizes into two unitaries. There's the micromotion operator, P of t, which is periodic with the same period capital T as the drive. And then there's a second unitary, which is generated by a time-independent operator, the so-called flow K Hamiltonian. And what I want you to know is that this flow K Hamiltonian is an effective object. It doesn't exist without the periodic drive. It doesn't exist on its own. Now, that's the mathematical theorem, but what's the physical meaning behind flow K theory? The physical meaning is that it gives us a special rotating frame, pretty much like this merry-go-round, such that in this rotating frame, the dynamics of the system is governed at all times, stroboscopic or non-stroboscopic, by the static flow K Hamiltonian. The flow K Hamiltonian also has an eigenvalue problem. In particular, the eigenstates are called flow K states, and the eigenenergies are called quasi-energies. But what I'd like you to appreciate here is that this operator is not unique, because what I can do is I can always shift the spectrum by an integer multiple of the drive frequency. And that's just because, as I said, the physical operator is this exponential. So this shift basically doesn't contribute to it. Another concept which will be very useful for us later on is the concept of the so-called flow K gauge, or in other words, the dependence on the phase of the drive or the starting time T naught. So what this tells us is that if I, for instance, drive my system with a sine wave or with a cosine wave, I will get a different matrix for the flow K Hamiltonian, and this matrix will depend on whether I drive with a sine or a cosine. This is denoted here by this square bracket. And so if I want to, if I have the flow K Hamiltonian, say, for a cosine drive, and I want to compute it for some other starting point or some other phase of the drive, what I will do is I will conjugate by this micromotion operator P of t. And what I want you to know is that because the matrix depends on the phase of the drive, the eigenstates, the flow K states, do depend on the phase of the drive. And in fact, you can change from one phase to another phase by this micromotion operator. However, the spectrum, the quasi-energies, are independent of T naught. And this is why I'm going to be using this notation with the square bracket to indicate that the matrix depends on this parameter, but the spectrum doesn't. So this is all very nice, but the question again is now, how do we control the dynamics of eigenstates of the flow K Hamiltonian? This is nice, as I said. However, flow K theorem doesn't tell us anything about how to compute this object. And so this requires either computing time-ordered exponentials, which involve special functions and can only be done in limited cases such as circular drives and harmonic oscillators,
or it requires some sort of perturbative expansion, like the high frequency expansion, where you basically make an ansatz for the flow K Hamiltonian, and then you expand the left-hand side to the right-hand side, and you collect terms, and you basically generate the entire series. This comes with limitations. In particular, the series have a finite radius of convergence, or it's sometimes also asymptotic. And what it physically means is that it fails to capture energy absorption processes. So it doesn't capture the flow K resonances. And so this brings us to the second question that I want to pose for today is, can we construct non-perturbative approximations to the flow K Hamiltonian? And in particular, I want an approximation that does not rely on diagonalization, so that it can be applicable in the many-body regime. And second, it also does not rely on time ordering. That is to say, I don't need to solve ODEs. To do this, I need to introduce a couple of concepts from adiabaticity. So just to remind you again, let's say that you have a two-level system, and this system has a ground state and an excited state, and your Hamiltonian depends on some parameter lambda here on the x-axis. And let's say that we start with the population in the ground state, and we change the parameters slowly. Now, if we do this in the adiabatic limit, where the ramp speed goes to 0, the ramp time goes to infinity, but I keep the product fixed, and I necessarily have the condition that my eigenstate is gapped, then I know that my system follows the instantaneous eigenstate of the Hamiltonian. What does it mean practically? It means that if I take an instantaneous eigenstate of h, say with parameter lambda 0, and then if I evolve my system with my Hamiltonian h of lambda of t, then I will find at later point in this adiabatic limit the system in the instantaneous eigenstate up to a phase. And as we know from quantum mechanics, the phase can, has two contributions. There's a so-called dynamical phase, which is the integral of the eigenenergies. But then there can also be a geometric phase, which is given by this expression here. Now, this is what happens in the adiabatic limit. But if you go away from the perfect adiabatic regime, you're going to create excitations. So what I want to do now is quantify where these excitations come from. So let's first take our Hamiltonian H, which depends on lambda, and let's just diagonalize it. So D is a diagonal matrix with the eigenenergies of the Hamiltonian. This is fine, but now lambda is a parameter that depends on time, and therefore, when I do this, I actually need to change the frame. So it's not just a static change of basis transformation. I also have to pick up a so-called Galilean term in that frame. And so now, in this new frame, I have a diagonal matrix, which is clearly, harmless. It cannot create any excitations. It's just diagonal. Therefore, all the excitations necessarily come from the second term here, which I'm going to call A, and this is the adiabatic gauge potential. So once again, the gauge potential is the culprit for all your trouble, for all the excitations. And just to bring everyone on the same page, you basically know this object. You've seen it before. If I compute the diagonal matrix element of the gauge potential, then this is just the Berry connection. Then from it, I can compute Berry phases, Berry curvatures, Chern numbers, etc. So this is an object that you guys have seen. You probably just haven't thought about it in this context. So once again, it's the gauge potential that creates the excitations. Now, if we want to do adiabatic dynamics away from the adiabatic regime, all we need to do is cancel those excitations. So we're going to apply a counterforce that basically subtracts the excitations with a mechanism that is shown here in this picture. Suppose you're a waiter and you need to serve a glass of water. However, you want to serve as many glasses of water as quickly as you can because this is going to maximize your tip, right? Your profit. And so what you do is you go very fast. But if you go too fast, you're going to spill the water, right? And then your customers aren't going to be that happy. And so instead, what experienced waiters do is they tilt the tray. So they apply a counterforce, and this counterforce basically cancels the excitations. This is exactly the concept of a counterdiabatic Hamiltonian. So the counterdiabatic Hamiltonian is our original Hamiltonian that we had before. And now we just add this term, this adiabatic gauge potential, such that if you would now go to the co-moving frame, this term will cancel exactly that, and you'll be left with something that has no excitations whatsoever. And so what this basically amounts to doing is it amounts to lifting the condition for the adiabatic limit. Now I can do adiabatic dynamics without being very slow. And this is really what is meant under shortcuts to adiabaticity. So you see here, this is exactly, if I now evolve with this counterdiabatic Hamiltonian, instead of just being in the limit, in the adiabatic limit at any time, at any speed, I'm basically guaranteed to be in the instantaneous eigenstate up to a phase. So now this is all nice, but I want to recall for you a nice, non-uniqueness of the gauge potential. So in particular, I can rephase my eigenstates by any phase chi, which depends on lambda. And what this means is that the Berry connections are going to pick up this additional term. And this is why they're not gauge invariant. What this means for me is that I can actually add to the gauge potential any operator which commutes with the Hamiltonian, and so the counteradiabatic Hamiltonian is therefore not unique. There is, however, one very special gauge potential, which is the so-called Kato gauge potential, which is gauge invariant. And the way it works is very simple. You just take the gauge potential the way we defined it on the previous slide, and you just subtract the non-gauge invariant term. It turns out that this is good enough, and it does the job. And for those of you who are used to thinking as the gauge potential as the derivative, then this Kato object is like the covariant derivative. Okay, so now I've introduced everything that we need to know. And what we are about to do is we're going to derive a relation between the Floquet Hamiltonian and the drive Hamiltonian as follows. So recall the definition of a Floquet Hamiltonian in this special rotating frame. What I will do now is I'll just take this p-Dagger operator and p, and I'm just going to throw it on the left-hand side using this definition. And so I get the following equation, where this I dt p-Dagger term is nothing but my gauge potential, the adiabatic gauge potential with respect to the phase of the drive. And so now, by just rearranging this equation, I get something really interesting. Namely, I find the following. My lab frame Hamiltonian, h of t, is the counteradiabatic Hamiltonian for the Floquet Hamiltonian. Okay, so let me unpack this statement for you. So let's just test this. Let's start with an eigenstate of the Floquet Hamiltonian, and let's just drive it with a counteradiabatic Hamiltonian. This is just this expression here. Now, by Floquet's theorem, I can decompose, my evolution operator into micromotion times the Floquet operator. The second term, however, this is an eigenstate of the Floquet Hamiltonian. Therefore, I pull out the quasi-energy phase, and then the micromotion operator just moves me forward to where I should be. So this is exactly the definition of a counteradiabatic Hamiltonian. But notice the subtle difference. The Floquet problem is actually an inverse counteradiabatic problem. So what this means is that we are given the counteradiabatic Hamiltonian h of t, and what we are after is the Floquet Hamiltonian hf. And this is kind of a very useful relation here in this box, because it tells us that, because we always know that the Hamiltonian that we drive with, if we can find this gauge potential, then we can also find the Floquet Hamiltonian. And this is basically the procedure with which I'm going to show you in a second, we can compute variationally that object. So now comes an equation that I cannot derive here because I don't have the time for it, but you should just trust me. So there's this function g, which is given on the right-hand side. And if I have the exact gauge potential, then this function vanishes. And I'm going to use this now to cook up a variational principle for A. The way to do this is to start with an ansatz for the kick operator with some operators that I'm going to choose myself, and some Fourier harmonics and some unknown coefficients k and l that I need to find. Then we're going to compute the gauge potential with the familiar expression. From this, we're going to plug the gauge potential into this function g. Now, these coefficients were random, therefore this function won't vanish. So I'm going to decompose it in the same basis that I started from. And then what I will do is I will update my variational coefficients k in the direction of the error for some small step size eta. I repeat this procedure, I iterate it until it converges, and then I'm basically done. So notice, this requires no diagonalization, and it also requires no time ordering, right? So let's see how well it works. Let's first take a system that we know how to solve. That's just a two-level system in a circular drive, one of a few examples that we have exactly the Floquet Hamiltonian, and we can compute all the objects. So what you see here on the x-axis is always time. And then there are four plots. There's the kick operator itself. There's the gauge potential. There's the Hamiltonian, this expression here. And then there's the corresponding Floquet Hamiltonian to that. And there are three curves, and the three different colors are the projections on the sigma z, sigma x, and sigma y operators. And so what you see here, in particular in this plot, is that there's a solid line, which is the variational solution. And then there's this dashed line, which is the exact solution. And we see that they match perfectly in this case. That's good. Let's do something more interesting. So now let's take a two-level system, which is in a linear drive, and therefore we cannot find a closed form expression for the Floquet Hamiltonian. So this is the Hamiltonian again. And once again, in this case, what we can do is we can only compute the Floquet Hamiltonian numerically. So we can do that. And on the lower right corner, you see the numerical result, which is the dashed line, coincides exactly with the variational result, which is the solid line. One thing I want to emphasize is that this is a resonant drive. And so being resonant, it's beyond any high-frequency expansion. It cannot be captured by high-frequency expansion. However, the variational approach is non-perturbative, and it does the job. Okay, two-level systems can't impress anyone with them, so let's do something more exciting. So let's do a many-body, non-integrable many-body chain. Here's the Hamiltonian, and I'm going to do the following now. For this Hamiltonian, I can first compute numerically the exact Floquet Hamiltonian, and this is my reference point. And then I can compute two further approximations. The first one is the variational approximation, where now my operator, my kick operator is expanded in the single particle and nearest neighbor two-body terms, and I keep up to 21 harmonics. So this is the variational approximation. But I know also how to compute the Floquet-Magnus expansion here, and that's another thing that I can do in order to compare. Once I have these different approximate Hamiltonians, then what I'm interested in is comparing the evolution operators, because these are actually the physical objects. And so I can compare the variational one to the exact one, and I can also compare the Floquet-Magnus one to the exact one. So let's see how that works. Now here on the right-hand side, I'm showing you such a comparison. On the x-axis, I have the Floquet gauge, or if you wish, the phase of the drive. And on the y-axis, I have such a norm difference between various operators. What you should know is that, good solutions are the one where the norm difference goes down to 0. So let's first see what the Floquet-Magnus Hamiltonian gives me. So the 0th order approximation are the orange dots. Then if I do the 1st order approximation, I get the green squares. It becomes a little bit better. But it's actually not as good as the variational one, which is this crosses. So the variational approach outperforms the high-frequency expansion. And what I'll do now is I'll fix myself here at this phase of 0, and then I'll do a sweep over the frequencies from large frequencies to small frequencies. And in all those cases, you see that the variational approach outperforms everything else. So we have a new way, a new procedure, how to compute the Floquet Hamiltonian in a non-perturbative way. But we can actually do better. Remember this gauge invariant Kato potential that I showed you? So in the same way, I can decompose my Hamiltonian as the Floquet Hamiltonian and the Floquet gauge potential. I can decompose it into a gauge invariant Kato potential and some other object. And I'm going to call this object the Kato Hamiltonian. The price to pay is that the micromotion is no longer periodic. So what's actually the physical meaning of this Kato Hamiltonian? Now, let's take the adiabatic limit. Now, this is a slightly different adiabatic limit where I sent the period of the drive to infinity, the frequency to 0. The ratio is kept fixed, and then I just very, very slowly time. So let's consider now the evolution of a Floquet eigenstate NF. I want to see which of the many different objects actually corresponds to the adiabatic Floquet evolution. So what's the adiabatic Floquet evolution? I apply my lab frame Hamiltonian to the Floquet eigenstate, and by Floquet's theorem, I just pick up a phase, and I end up in the corresponding translated eigenstate. Now I can do the same thing with the Floquet Hamiltonian. So now I'm doing an adiabatic evolution of a Floquet eigenstate with a Floquet Hamiltonian. Clearly, I'm going to pick up the quasi-energy phase. But this is now adiabatic. So if there's any geometry in this state manifold, I'm going to also pick up a geometric phase. So you see, the Floquet Hamiltonian doesn't generate adiabatic evolution with respect to the Floquet states. However, the Kato Hamiltonian does exactly that. And the reason is that the spectrum of the Kato Hamiltonian conspires. So these dynamical phases conspire with the geometric phases in exactly the same way as to give us the quasi-energy phase. So therefore, one can conclude that it is H Kato that recovers the correct Floquet adiabatic evolution and not the Floquet Hamiltonian itself. So now I, promised, like make a big statement, and I want to show you this and how that works. So the statement is the following: Floquet's theorem follows as a special case from the adiabatic theorem. And in fact, we've already shown this. I just want to go over the equations again. So let's start with the adiabatic theorem now for a periodically driven system. And I want to cast this theorem in counteradiabatic form. So the theorem states that the lab frame Hamiltonian HFT generates adiabatic evolution with respect to the Floquet eigenstates. So let's go to the co-moving frame where I know that I have no excitations. In this frame, this is exactly the same frame where the dynamics is given by the time-independent Floquet Hamiltonian. And in that frame, I know that the evolution operator is just, given by the Floquet Hamiltonian. But if I go back to the original frame, I know that I have to transform back to it. And therefore, I get that the evolution operator in the original frame is, this evolution due to HF times this transformation. And this is exactly the content of Floquet's theorem. So you see how you can derive Floquet physics from the adiabatic theorem. But we can do better. We can get a gauge invariant formulation of Floquet's theorem by using the Kato decomposition. And so in that case, this is a little bit more involved, and I'm happy to discuss this offline if there's anyone interested. But just to show you that you can really drive this analogy further, and you can actually really get something new out of it, let me make a second statement, which is the following. So we can now explain quasi-energy folding as a consequence of a broken U1 symmetry of the adiabatic gauge potential. So this is a very complicated statement, so let me unpack it for you. So first of all, what is quasi-energy folding? Well, as you guys know, in static systems, the energy axis is unbounded from -infinity to +infinity, but in those periodically driven systems, when I look at the Floquet Hamiltonian, it only occurs under the exponential, and therefore my spectrum is wrapped on the circle. So this is quasi-energy folding. And because of this, I know that if I shift my quasi-energy by an integer multiple of the driving frequency, I go back to exactly where I started. So let me now show you how this leads to the statement above. So let's reconsider the U1 gauge transformation of the eigenstates. I'm going to rephase the eigenstates, same way as before, but the Berry connections are not gauge invariant, they pick up this shift. However, if I look at this relation, the left-hand side is the lab frame Floquet Hamiltonian. This is a gauge invariant object. So if the gauge potential is not gauge invariant, then it means that this freedom here has to be absorbed exactly by the Floquet Hamiltonian. So now let's take, an eigenstate, and let's assume that it is periodic, like Floquet eigenstates are. Then what this means is that the most general form for this phase chi is just something that wraps around times, some arbitrary Fourier series with some unknown coefficients AL. Now let's compute the dt chi. If we do that, then the time dependence here goes away, and then the sign becomes a cosine. But notice something interesting now. This term here is exactly the expression for the quasi-energies. And we know that quasi-energies are time independent. However, we're trying to gauge them with something that is time dependent now. So obviously this is not going to work. And the only way that this gauge transformation can make sense is if, this term here where the time dependence comes from actually is 0, which means that all these coefficients AL have to be 0. As a result, the only leftover gauge freedom is that dt chi is equal to m omega. And this is precisely the transformation that we have in the quasi-energy folding. So as you can see, it is periodicity that breaks the gauge group from U1 to Z. But now it's really cool because, we've understood, where this folding comes from, and we've connected it to this residual gauge group symmetry. And I just showed you on the previous slide that I also have a gauge invariant formulation. So can I actually find then an unfolded Floquet spectrum and a Floquet ground state? I think the answer is yes, but this is something that we're currently investigating. In the last 3 minutes, let me just very quickly give you one application of these counterdiabatic Floquet drives. So let's say that you have a transoscilled Ising model, and what you want is you want to start from the paramagnet here, and you want to prepare the ferromagnetic ground state. And the only constraint that you have is that you can only use XY fields. Now, if you do the naive thing where you just ramp through this critical point here, what you find is that the fidelity as a function of time drops drastically, and eventually you lose pretty much all of the fidelity. This doesn't, it doesn't matter which ramp you use, they basically give you the same thing. But what if you had another direction? What if you could turn on a Z field? Now, you have no access over the Z field, but if I had a Z field, then I could circumvent the critical point and get to where I wanted to. And the trick now is to use Floquet engineering in order to set up such a Z field. So the way to do this is to introduce a circular drive in the XY plane. If I now go to the rotating frame, then I pin the drive, say, along the X direction, but I also have this Galilean force, if you wish, a centrifugal force. And this centrifugal force gives me exactly this additional direction, now coming alone from the frequency of the drive. However, if you do, this is the red curve now, it doesn't really buy you much. So it gives you only a marginal improvement. And what you have to do is you have to do counterdiabatic driving. So if you cancel now these excitations, and these are now excitations in the Floquet states, by adding the gauge potential to the Hamiltonian, then we get the blue curve. And as you can see, the fidelity becomes much better. And so the inset here shows you the fidelity as a function of the system size. And you see, that the prefactor, we basically gain almost an order of magnitude improvement compared to the adiabatic ramps. All right, so let me come to the summary and let me reiterate again the take-home messages from today. So again, the lab frame Hamiltonian generates counterdiabatic driving with respect to Floquet states. As a result of this, we can show that Floquet's theorem follows as a special case from the adiabatic theorem. As a consequence, we can explain quasi-energy folding as a consequence of a broken gauge group of the adiabatic gauge potential from U1 to Z. And something that is actually a little bit, looked, it's overlooked very often is that we've shown that adiabatic driving does not require a Hamiltonian because the Floquet Hamiltonian is only an effective object. It's unphysical. It's only the unitary that is physical. And in some sense, you can push this further and you can say, it doesn't need energies. It only needs the geometries of states. We've seen also some implications of this. So in particular, we can derive non-perturbative variational principles that do not require diagonalization, do not require time ordering. What I didn't mention because I forgot was that, this comparison, for the many-body system was done for 12 spins. I also had the variational data for 16 spins. I couldn't compare it because I couldn't solve, the time ordering for 16 spins. So you can really push in the many-body regime with this variational principle. But what we also have seen is that counter-adiabatic Floquet driving can be very useful for controlling Floquet-engineered matter. And we actually have a paper on this with a bunch of other applications to topological state, etc. I'd be happy to talk about this. And so, when it comes to the outlook, there's this very interesting gauge invariant formulation of the Floquet theorem now in Floquet physics. I mentioned that there should be a Floquet ground state because we've solved essentially the folding problem. Now, the next question is, are those kata objects here local, right? So can they be used? Do they contain physical information? We've already seen that they are the HK, at least is the adiabatic, is the proper adiabatic object. And then I'm interested in, potential extensions beyond driven systems like quasi-periodic drives or maybe some general time dependence. I'd like to thank you for this and for your attention.
So, thank you for this nice talk. So, if you now have this variation of law that the cable you made this ansatz for the cable component. Isn't sort of making the local ansatz similar constraint that are frequency approximation?
Not necessarily.
So, last question, if you not take into account the global difference in this expansion, just few of them, if you do already something with few of them.
Yes.
Instead of all of them, which you would,
Exactly. So the first question, you're exactly right. So if you only take these local terms in your ansatz, then as you can see, when the frequency becomes sufficiently low, then your approximation is not great. What this tells is that you do need the non-local terms that you mentioned. So there's no free lunch in terms of that. Now, to your second question, can you actually put in, some non-local terms and then get something that's much better here with only a handful of terms and not all of them? The answer to this is yes. Because this is a variational approach. For as long as you know which terms to put in, or you have a procedure that you can exhaust a few of them and then try them out, then this is actually going to work. Yeah. So Floquet theorem applies to linear systems. Which kind of nonlinearity do you have in mind? If you think about an A dagger, AA, that's okay. That's linear because your Hamiltonian is a linear operator on a Hilbert space. So it applies, this is all in, right? Like whether I call it a non-integrable Ising model or a Bose-Hubbard model, this is basically very similar. Oh, this is all the same. Yeah. To the order of, there is no need to. So to the order of the approximation, these are the same. In fact, this guy here that you see, this kick operator here, this is the Van Vleck kick. And it automatically somehow figured out the Van Vleck kick and not the Floquet Magnus one. Yeah. Can you speak up? Sorry. Yeah. So what relies on the hermiticity of the Hamiltonian is the formalism of counter-adiabatic driving. That thing people have tried to extend to open systems, and in particular non-Hermitian systems. And as far as I know, it hasn't been done yet completely. And the problem is that you have to deal with left eigenstates and right eigenstates, and you have to figure out what to do with all of that. So the moment this problem is solved, I believe the connection will hold through, because Floquet theorem doesn't require hermiticity. Yeah. I think I need to stop sharing. Hold that.